Today we will see some examples of uh, categories uh, and some properties and new some definitions like subcategory and uh, other things. Okay. So, so we have uh, said that a category consists of a class of objects, right? Uh, with some other things, right? So if that class of objects, if that class, so what is the meaning of class? So class is actually any collection, right? So if that class of, so uh, so if the class of objects in the category C is a set, then the category is called a small category. So we allow the class of objects to be any collection, right? Well, it may be a set or it may not be set, but if it is a set, then it is called, the category is called a small category. Uh, so an example of a category in which the class of objects is not a set is the collection of is the category of all sets. So in the category of all sets, the class of all objects is not a set. You know that set of collection of all sets is not a set. So that uh, so given any category C uh, and any object X, an object in C, for every object X in C, there is a a morphism. So this is morphism, a morphism of X, which is called identity morphism. So uh, it satisfies following property that if f from X to Y and G from Y to X is any morphism, then Ix composed F equal to F and Gx equal to G, right? So this is the condition for Ix to be an identity morphism. So identity morphism is unique. Is unique. Suppose let ix and ix prime be two identity morphisms for an object x in a category C. Then what we have is ix prime equal to ix, also ix equal to ix prime. So that condition, you can see that this ix composed f equal to f and g composed ix equal to g. F was from x to y, g was from y to x, right? So here, in the first case, what we have done, we have taken f equal to f, we have taken as ix, right? X equal to y, we have taken x equal to y, right? And g we have taken here as ix prime. So if we do that, then from this and this, from this we have this one, and from this we have this one. But this, you see, this is same as this, and hence ix. So ix. Hence identity morphism is always unique. Uh, Next, if f from x to y is any morphism, then a morphism g from y to x is called a left inverse of f if f compose g equal to ix, identity morphism for x. In this case, f is called left inverse called left inverse of f if this is there. In this case, f is called a right inverse of f. G, inverse of g. A morphism g from y to x is called an inverse or two-sided inverse if G equal to Ix and G Iy. If this is there, then we have this. A morphism f from x to y is called an balance this called an equivalence if it has a two-sided inverse. Next, we have following lemma. If a morphism f from x to y has a left inverse and a right inverse, then they are equal, and F is an equivalence. Proof. Select G1 from Y to X, G2 X be left and right inverses of F respectively, right? Beyond so that G1 equal to G2. So let us see how we are going to do. So we have G1 post I y equal to, this is here, G1 equal to this, right? This is property of identity morphism for y. This is this equal to this, and this is your post because your G2 is a right inverse of F. We have G2 and this is equal to G1 F G2 because by using associativity, of the composition category. And this is what, because G1 is left inverse of F, G1 F compose G1 is nothing but I X compose G2. And this is what, this is basically again by using property of identity morphism for X, this is nothing but G2. So G1 equal to G2. So this completes the proof. So hence G1 equal to G2 is a two-sided sided uh, inverse, is a two-sided inverse of F, and F is an equivalence. So by using this lemma, we conclude that observation if F from X Y is an equivalence balance, then then uh, it has a unique uh, inverse F inverse from Y to X. This is just simple observation. You can try to see this. You can take two different inverses, right? They will be right as well as left inverses, and then you can conclude. Now, if uh, X, any two objects X and Y are called equivalent, equivalent denoted by if there exists an equivalence F from X to Y. Uh, this is another observation. Uh, the relation of equivalence and the class of objects is an equivalence is an equivalence relation. So this you can verify. This is simple observation. So you take any category and its class of objects, right? So you can denote maybe by this. And then for any two objects x and y, you define x is related to y, right? X is related to y if there is an equivalence from x to y, right? Then this relation is an equivalence relation. You can verify. So if x is equivalent to y and y is equivalent to z, then x is equivalent to z. The reflexivity will be there. Given any object x, x is related to x because the identity morphism ix is there. Reflexivity, so reflexivity is satisfied, then symmetry. So if x is related to y, right, then there will be some equivalence f from x to y, but then f inverse from y to x also will be an equivalence. Hence, this relation is equivalent relation. Next, uh, we see some examples of categories. So, examples. First example, the category of sets and functions between them, right? So, consider the class of all sets, right? Right? And between given any two sets, uh, consider this to be set of all functions from x to y. For any two given sets x and y, home xy consider as the set of all functions from x to y. And then composition, you can consider visual composition of functions and identity and all will be visual. So this will be a category. Second, the category of topological spaces and continuous maps between topological spaces. So this also is a category. So in this class of objects will be uh, all topological spaces, and given any two topological spaces x and y, home xy will be uh, set of all continuous functions from x to y. Uh, yes. Then third is the category of groups and homomorphism. So in this category, a class of objects will be collection of all groups, and given any two groups X and Y, home XY will be set of all homomorphism, group homomorphism from X to Y. Again, here composition is usual composition of functions. Next is the category of R modules. R is any ring. R modules and module homomorphisms. Homomorphisms. Then fifth, the category of sets and injections. Injection means injective functions. Injections or surjections. Jections or bijections. Right. So this is a category. So let us discuss this one bit more. So first you consider the class of objects as all collection of all the sets, right? Then given any two sets, consider home xy as collection of all injective functions from x to y, right? So it is possible that there is no injective function from x to y. In that case, home xy will be an empty set, right? And again, composition will be usual composition of functions. So you know that if you have two injective functions, their composition also is an injective function, right? So this will give you a category. Next, in this uh, home xy, you can take collection of all surjective functions from x to y, right? Then that will give another category, right? Keep the class of objects same, that is the collection of all sets, and then home xy you change to be the collection of set of all surjective functions from x to y. Again, it is possible that there is no surjective function from x to y. In that case, home xy will be empty set. Similarly, you can consider home xy to be set up all bijective functions from x to y, right? That will give another category. So basically, these are yeah. So we will see after some time that 5 is a subcategory of this category of sets and functions. Next, the category of pointed sets. Category of pointed set. So what is a pointed set? A pointed set is a non-empty set with a distinguished element. Category of pointed sets and functions preserving distinguished elements. Distinguished elements. So like you consider the collection of all sets, right, non-empty sets, together with some specified, some distinguished element, right? So for example, with X you can consider this, right, non-empty set. So this small x should be an element of capital X. Similarly this, right? And then home X and then Y. What will be this? This will be uh, set of all functions f from x to y such that fx goes to y, right? So it preserves the distinguished element. So distinguished element in capital X goes to distinguished element in capital Y. So if you consider home to be this set, then you get another category. Now we have another example of our category. This is the category of pointed topological spaces. That is, what is a pointed topological space? A pointed topological space is a non-empty topological space with a base point. What is that base point? That is a distinguished element. Right? So a non-empty topological space with a distinguished point is called a pointed topological space, and that distinguished point element is actually called base point. Pointed topological spaces and continuous maps preserving base points. Continuous maps preserving base points. So this will give here if x and y these are pointed topological spaces. Then if we consider home this to be collection of all set of all continuous functions from f from x to y such that fx equal to y, that is base points are preserved. Then this will give a category. Then eighth, the category of all finite sets and functions. This will give another category. And then last example I give, uh, given a partial order this in x is any set, there is a category, a category whose objects are elements of x and for any xy in x, home xy is either singleton, either it is a singleton set consisting of the ordered pair xy are empty according to whether x is less than equal to y or x is not less than equal to y. How we define composition? So if xy is in home xy and yz is in home yz, then the composition, right, of this and this will be actually xz, and it will be in home xz. Why? Because x is less than equal to y and y is less than equal to z, and hence by using transitivity of the partial order relation, x will be less than equal to z, and hence xz will be in home xz, and that will be the only element in home xz. Now if home xy is empty, then there is nothing to compose with yz. If home xy, similarly, if home yz is empty, then there is nothing to compose with xy, right? So if home xy and home yz are non-empty, then we can compose, and composition will be like this. So today we will stop here.